Hello students, welcome back to Tuition Masters, and today we are here with a one shot revision for grade 10 CBSE magnetic effects of electric current. As you know, this chapter is coming in your term 2 exams which are very near. So in Tuition Masters I'll be taking your magnetic effects of electric current, electricity, then carbon and its compound and periodic classification of elements in the upcoming videos. So today here we are going to start with the quick revision of magnetic effects, and in the next session we will be discussing some important questions of the same chapter. Then we'll start with chemistry. All right, so what are we going to study in our today's lecture? Magnetic field and field lines, magnetic field through a current carrying straight conductor, magnetic field through a circular loop, and even a solenoid. After that, force on current which is carrying conductor plays in a magnetic field. Then about the DC motor and electromagnet induction, EMI, Faraday's EMI. I'm going to even show you a simulation of this EMI, Faraday's EMI, at the end of the session, so stay tuned till the end. So first of all students, here is a very quick mind map of the whole chapter which you can just have a quick look before, like 5-10 minutes of your final exam. You should take a printout and save it with you. This is a whole mind map for the magnetic effect of current. What is magnets, types, properties, then what is the field carrying solenoid, everything I have explained over here. So you can just take a screenshot, save it, draw it, however you want to do. Now students, when I talk about electric current, electric current, so you have been studying about electric current since grade 7. Since grade 7 you all have been studying. How? Firstly, if you all remember, in your 7th standard you might have studied the heating effect, of electric current, correct? Heating effect. After that, in grade 8 you might have studied the chemical effects, correct? Chemical effect. And after that, not in ninth but in 10th, you are directly studying the final effect, which is the magnetic effect, correct? So this was these three effects were taught to us, correct, when we started with grade 7, correct? So heating, chemical is done. Now in this standard you are studying about the magnetic effect. So heating effect, for example, take in bulbs, you studied about filament, you studied about tungsten and various other heating effects. After that, you even study about the chemical effects, for example, electrodes, electrolysis, electroplating. Then you study about anode, cathode, anions, cations, right? And in 10th we are going to study the magnetic effect of electric current. So in total there are three, and this year you are completing the third one also. So electric current is full on done. So first thing of our chapter, the most important thing of the first basic topic of our chapter is Orsted's experiment. Who is he? His full name is, okay, I'll change the pen color. Okay, his full name is Hans Christian Oersted. Now, he was the first person to discover the magnetic effect. How? With the compass needle deflection. In your 7th standard you might have got just a very quick glimpse of this his experiment. So compass needle deflection, due to this experiment Oersted had found the magnetic effect. What did he do is that he took a battery, then he connected the wires properly, and he even took a compass. Now, whenever the circuit was switched on, whenever I switched on the circuit, what happened if I took this, what do I say, if I took this compass near to the wire, near to the circuit, what happened? There was deflection visible. What happened? Deflection was visible on the needle. The needle is like this, but then it changed, it deflected. This is what Hans Christian Ørsted had found out by his experiment. By mistake, it was not accidentally. Like okay, it was accidentally. He didn't do it by purpose. It was accident. He took that compass by mistakenly there, and it started to deflect. Then he started to study about that as well, right? So we got to know about the magnetic effect. So what did it prove? What was my observation with this? With this accidental activity, what was my observation? My observation was that there is electricity and magnetism. Electricity, magnetism were interrelated to each other. Correct? Electricity and magnetism had some relation with it. That is why the needle works on the Earth's magnetic force. Correct? But it changed the deflection. It changed the angle. It changed it. It deflected. Why? Because it was when near the electricity. So electricity and magnetism for sure had some relation. Okay. Now, next is magnetic field and field lines. Now, you might have done this experiment in your previous grades. You might have got iron fillings. Okay, iron fillings you take. You can even try it now also. Today as well, you can try it out. If you have iron fillings and a magnet, just these two things are required, nothing else. Do one thing on if you have a glass table, take a glass table. On that, just randomly pour the iron films, okay, and then keep this magnet underneath it. Okay, keep the magnet. What will you see is that on the north and south there will be such kind of pattern. There will be such kind of patterns observed. See, how is that pattern, like what is the diagrammatic structure of it? So, if you check in this figure carefully, if I want to do the markings on this, it is even clearly visible by the iron fillings. If I do the marking over, there is some kind of field lines like this. Like this, if you see carefully, you can observe that there are field lines made. Correct? By the iron fillings. How is it so? Automatically happened. No, we didn't keep it like this. It automatically happened that it formed such a structure. So what is the structure? These are nothing but the field lines. By the, if I'm taking near to that, I'm taking my mirror, not mirror, magnet near to the iron filling, they automatically form such a pattern. You place it anywhere, you place iron fillings anyhow, but they will automatically come on this kind of direction on the north and south poles. So what are the properties of these field lines? Magnetic field line, what are their properties? Property number one: magnetic field lines emerge from the north and emerge at the south. Remember, what is it? From north at south. Correct? Means they start from the north. From here, from the north, these magnetic fields will start and they will flow towards the south. They will the magnetic fields from everywhere, they will start from the north pole, north side, but they will come and emerge at the south. Okay, so if this is my magnet, this is my magnet, take suppose this is north, this is south. So what will happen? Always they will come like this, like this. From here it will go. From north it will come to south. From where will it come? From north it will come to south. So property number one is that magnetic fields always start from the north and come to the south. Again, it can come for your MCQ questions. Property number two: inside the magnet lines goes from north south to north. Now see this, there is some kind of confusion kind of thing, but don't get confused. See, inside and outside both we have. Correct? Now when I talk about the exterior part, when I say magnet from outside, what happens that it is that the magnetic lines are moving from north to south outside, but from inside the magnetic lines are going from south to north. Okay, from south to north they're coming like this, they are going like this, but from here it goes back like this here, and it again comes back to here. So understand that. Again, let me draw the magnet here. See this, this is my magnet. Okay, what is happening is, let me change my color. Take suppose this. Now the field lines are starting from the south only. From the south it's going to north, but inside the magnet. Then from north outside it's starting again. From north, it's starting from outside again and reaching to south. Okay, again similarly here also down also it's moving and going to south. But actually inside the magnet it's going from south to north only. Outside it goes from north to south. So just understand that, don't get confused. Next is property number 3. Magnetic fields are crowded near the poles. Property number 3 is that they are crowded near the poles. I'll show you that iron filling thing again. Can you see this? Can you tell me at which place the iron fillings are more in quantity? Here, at these places. What are those? They are nothing but poles, correct? Okay, I'll change the pen. Okay, there were poles. So at the poles there is more quantity of ion fillings compared to the remaining place. So that's why all these magnetic fields are always more near the poles. Here also you see in the diagram, see, it's more where? It's more near the poles, and always it will be near to the poles only, most of them. Okay. Next is concentrated at places where magnetic field is strong. They're concentrated, they're starting from those places where there is more magnetic field, the strong magnetic field is there, it will be concentrated there. And there are spread apart at places where magnetic field is weak. They will come together where there is strong field, and they will go far when there is weak the magnetic field is weak. Now again let's come to this example. It is the previous one. See this. Now look at here carefully what I'm explaining. Here, this is the pole. At poles they are the most. Now here when they're starting, here is the strong point, so they are concentrated. But here when I talk about this part, this is weak part, so they are far away from each other. Here they are far, when the like field lines are far, so that means it is weak point. When they're concentrated, that is a strong point. Okay, so this is what we studied. All these points we have covered now. And the next property is that magnetic fields will never ever intersect each other. Okay, one very important and easy property also, that they will never intersect each other. That is nothing to explain because they're moving like this way, so they won't ever intersect each other. Okay, so these is a quick summary. All the 5 points are mentioned over here. So let's move towards the next topic, that is magnetic field through a current carrying conductors. When there are conductors also, what is the magnetic field actually? Now say that when current is passed through the straight wire, iron fillings arrange in concentric circles. Now what we are doing here is that I'm again using my iron fillings and I'm using my straight wire. Now straight wire is what? Straight wire, take suppose it's made up of some conducting material. Okay, it's made up of some conducting material. So that straight wire, when I take it near to the, when current is passed through the straight wire, what will happen? It will turn into a temporary magnet. It will turn to a temporary magnet. Correct? It turns a temporary magnet. So what will happen? The iron fillings are arranged in concentric circles. In concentric circles like this, they are getting arranged. Not in such form. Not in such form. They are starting to go in concentric circles. Like here, if there is a straight line, the current is passing like this, concentrically. Concentric circles are being formed. What are these? They are nothing but the field lines only. They are nothing but the field lines only. Okay. So, magnetic field lines are concentric circles around the straight conductor. Straight conductor, here we took a wire. If you take an iron rod also, if you take a copper rod also, anything, but it should be straight. So, like this, the circular kind of concentric circles will be formed. Those will become the magnetic fields. Okay, it will be the magnetic fields, like they will be in the form of concentric circles when a straight conductor is passed through them. After that, we get to know by the right hand thumb rule, the RHT rule. You can remember RHT rule, right hand thumb rule. How can you do it? Let us understand. See this. The thumb, if I'm holding the, like suppose I'm holding a pen right now. Okay. So when I hold the pen this way, it looks like that. Take suppose I'm holding that straight conductor. Like this I'm holding it. So what's happening? This is my curved finger and this is my thumb. So what can I infer from this is that the thumb, this direction it shows the thumb, so that direction the current is flowing. Okay, and the curled fingers, these are my curled fingers, they will show the direction of field. Very simple, right? So current is going up, but the how are the field lines going? They are going in circular way, they are going in circular way around the rod. Correct. So this is how you can remember the RHT rule, right hand thumb rule. Okay. Now, so what are the properties? So not property, let's quickly summarize. So what did we study? Magnetic field around a straight current carrying conductor is in the form of concentric circles. When I say there is a straight conductor, so the fields will be concentric circles. The direction of the field and the current can be found by the RHT rule, right hand thumb rule. And if I have a straight conductor, if I hold it like this, the curled fingers will show the field, and the direction of the thumb shows the current. Okay, so I hope this topic is clear. Next topic is magnetic field through a current carrying circular loop. Now, if I have a loop, how will it do? So don't worry, we have a picture also here. Now say that I have previously I was using a magnet. Now I am using not previously, last to last I was using magnet. Last I used a straight rod. Now I'm using a conducting loop. Now what will happen in the loop? So when current is passed in the past, so the iron fillings arrange in concentration. What again the same way? No, not that way. What happens is it comes like first is the straight way, first is straight, and then they start in like this order. Like this, they start to form their shape like this, and then they make circles at these poles. They will start to make circles at the poles like this, like the circles will start making. So this is about the loop. Here if you see, magnetic lines of force are concentric around the conductor. So if I have a loop, so here this way it will go straight, then it will start to curve, it will start to curve and form circles near the poles of the loop. So that is how the magnetic fields are there in a circular loop. What is the direction of field? Now again important, how will I find the direction? Previously I found by the RHT rule. How will I find? Is there any rule here also? Yes, we do have a rule, why not? So here circular loops can be considered as a collection of straight conductors. If I have a collection of straight conductors, I can say that that is the circular loop. Simple, right? If I have many straight conductors, if I join together like this, so I'll get a circular loop, right? So if the current flows in clockwise manner, so magnetic pole is south, and if the current is an anti-clockwise manner, so the magnetic pole is north. If it is like this is the magnetic field, it is anti-clockwise. Or if it is like this, so it is clockwise direction. So here this is the how we can determine the direction of field in a loop. Okay, now next one, fourth one is the magnetic field through a current carrying solenoid. Now, solenoid we have. First, what did we do? Magnet. Second, straight rod. Third, current carrying loop. Now we are doing a solenoid. Correct. So I hope students you know solenoid. Correct. When we wrap it around magnet, then we copper copper wire I'm making in form of spirals, solenoid. So you might have studied in grade 7 also, in grade 10 also. So that is a solenoid. So what is magnetic field through this now? So when I have a solenoid, it is connected to a battery, electric current flows and magnetic field is produced. Again, it is conducting, so yes, magnetic field will be produced. How? So when I say about the magnetic field, it is something like, it's a bit odd kind of thing you can say. First they will form like this. Okay, change color. Okay, they will go like this in a bit curved way, and then they will start making circles from the up side and even down. So like this they will start making circles. So let me also draw solenoid and explain you. So see this, say suppose this is my thing. Now solenoid I'll draw here. So see, if I want to draw solenoid, let's say that I'll draw this way. Just Yeah, these are my, this is my solenoid with the loops. What will happen is, I'll change the color. See, they will start going like this. They will a little bit curved also, little bit curved, and then they will make like these circles, like these circles. See, you can see that diagram also is there, right? So this is how the solenoid will carry the magnetic fields. Now, how do we find the direction again? First, we did the RHT rule for the straight wire, straight rod. So, how do we do for this one? So, this one we again have one more rule. What was that rule? That is again the thumb rule only. Hold it and see it. So this is my solenoid, correct? How do I do it? What you can do is that firstly, hold the solenoid, like act, don't hold it actually, just act as if you're holding it. Then compass south attracted to the north electromagnet pole. So the compass, the south one, it's showing the electromagnet pole, and the other one is showing, the thumb direction shows the north magnetic field. The thumb, this thumb will show the north field, okay, and the compass will show the electromagnetic pole, and this coil will be your, the current, okay, coil will be the current. This is how you can identify again the thumb rule. What will be the polarity? Now when I talk about the polarity of the solenoid, what will be, it will be by clock face rule. Okay, clock face rule. What is the clock face rule? So like this, if this is the condition, south. If it's going like this, north. So here you can identify, here the place, the polarity, how will it be? By the clock face rule. So what did we study? What are the factors now? So factors which will affect the magnetic field. Now in any conducting thing, whether it be rod, whether it be magnet, anything, how can I understand that I want to make it strengthen? How can my magnetic field be strengthful? First one is in solenoid. Okay, sorry, it's not about all, it's just a solenoid. So first one, if I number of turns in the solenoid, if I these here, if you see these loops, these ones, the coils which you see, these coils, if I increase them, so there will be more magnetic field, and it can be increased by increasing the current also. If you increase the current, so more magnetic field. Or if you insert a soft iron core, if you insert a soft iron inside the solenoid, again the magnetic field will increase. So this is how you can increase the magnetic field in a solenoid only. Okay, in a solenoid only. Now, next is force on a current carrying conductor placed in a magnetic field. So, what will be the force of current which is carried by a conductor and it is placed inside the magnetic field? So, say here that there is a current is flowing from in this rod AB, okay, A from BA, it's flowing from A to B, the current, and the magnetic field is induced in the conductor AB. Conductor AB is there is the current is flowing, and I have placed one magnet also in between them. What will happen now? So to find the direction of force, we use the Fleming's LH rule. So this is nothing but, you can say, FLH rule. Fleming's left hand rule. RHT rule was right hand thumb rule. This is FLH rule. Fleming's left hand rule. How? If you will place your hand like this, so the above one, your thumb, direction of force will be shown by your thumb, and the remaining fingers, the first finger will show you the magnetic field, middle finger will show you the direction of current. Okay, so direction of force is thumb, then the first finger shows you the magnetic field, and the middle finger, the second middle finger shows you the direction of current. So this is the FLH rule. Okay, now here conductor, it will move away from the magnet, and it is not like attraction repulsion. What will happen? The conductor, whatever it is, it will go away from it, it will try to go away. So when the direction of magnetic field reverse, if I reverse it, here it is south and north, south is above, if I reverse it, then I make it north south, what will happen? The direction of movement also reverse, the entire, this thing will be totally reversed, it will get reversed. Similarly, if the direction of current reverses, what will happen? Field will also be reversed and the movement will also be reversed. So in total, everything get reversed. So, direction of force applied by a magnet is affected by which two factors? First one is the direction of magnetic field. In which direction my field going and in which direction is the current going. With that, the direction of force applied by the magnet is determined. Okay, and factors which affects the Lorentz force. Now, what is Lorentz force here? Let's understand about that. So, when I say about the Lorentz force, what is that basically? It was firstly, who was it? The person was Hendrik Anton Lorentz. Okay, so this was the person basically, and he was a Dutch. Yes, he was a Dutch physicist. Okay, now what did he do was that he gave the formulated a formula for the force which gives rise to the electrical as well as magnetical fields. Correct. So, what was this Lorentz force all about? According to the Lorentz force, sorry, how do we define it? That it is the force, it is nothing but the moving force on moving charges, you can say. Yes, moving charges due to the electromagnet field, due to the electromagnet field. Okay, so due to the electromagnet field, the force on these charges was the Lorentz force. So you do force, you don't have to just remember more about, just remember what is the Lorentz force. Now, the factors which affects is the electric current first, magnetic field second, and length of the conductor. So these are the three things: electric current, field of magnet, and the length of the conductor affects the Lorentz force. So how do I formulate it? Firstly, the force is proportional to I. What is I over here now? It's nothing but, so I is the electric current, B is the magnetic field, and L is the length. Okay, so we can say that the Lorentz force is proportional to IBL. Okay, and F, the force is equals to K. K is nothing but a constant of proportionality in my proportions. Correct. So F is equals to BIL becomes the entire formula of Lorentz force. Okay. Now, the next thing, the second last thing of this chapter is the DC motor. So, DC motor, in, I guess, if I'm not wrong, in a 7th standard, you might have done the electric bell. Yes, electric bell, you might have studied the construction, the structure, and working of the electric bell. This year, you're going to do about the DC motor. Now, DC motor, you all might have seen what is the working principle. First of all, the force on a current carrying conductor in a magnetic field. So there is force which is there on a current carrying conductor. In the magnetic field, there is force applied. That is the working principle, and that's how it moves. What are the construction thing? What are its what? First, there are magnets in it. There is a armature coil. Again, a coil is there. Next, there is axle, then there is a split ring, brushes, and electric circuit. So this is how your structure of the DC motor. So the DC motor structure looks like this. This is how the construction is done. Now, how does it work? You can look here at this animation. You can understand how does it looks. So with the help of the electric currents and the magnets which are placed inside, these magnets which are placed inside, due to that it moves and it can provide the rotation thing. Correct. So like this, the fields are also applicable. Okay, so this is the working. Now, next thing is what affects this rotation. Rotation, now basically, why does it rotate? We attach some fan or anything to that small fan to the front part of it, so it rotates. So what is this rotation affected by? First is the strength of the magnetic field. How strengthful it is, how strong it is, that much rotation can be applicable. Next is the current in the coil. Through the coil, how much current, how much amperes of current is passing through, that also affects. And the number of turns, how many turns are made, that also affects the rotation of the DC motor. Now, next is, last is electromagnet induction, which is also known as EMI, electromagnet induction. Let's study about it now. Now, Faraday's law of EMI. Who is Faraday's? Faraday's is nothing but his full name was Michael Faraday. Okay, and he had given this electromagnet induction and its concept. So, what was this? It was a law. Okay, Faraday's law of EMI. EMI was electromagnet induction. So, when there is a movement magnetic field, it is linked to a conductor. A voltage is induced in the conductor. So when I say that there are magnetic fields are moving, and if I link it with a conductor, there is some amount of voltage which is induced. I'll be even explaining this law of electromagnetic induction with the help of simulation also very soon. Now, when I say the switch is turned on, if I turn on the switch, what happens? Magnetic fields are changed, they are generated, and the galvanometer will show the deflection. So the galvanometer which is there, it shows the deflection. You can look in these two images here. And after a while, there will be no change in magnetic field. So the deflection in the galvanometer is back to zero. So after some time, there is no change in the magnetic field then. So there will be no deflection also. And then the galvanometer comes back to zero. So this was the law of EMI. And the factors affecting the magnitude of this current is what? First thing, the strength of the field again. The field strength is the most important thing. How strong it is, that much factors is imputed here. Next is motion of the magnetic field. What is the motion of it? That also matters. And the length of the conductor again. Whatever the conductor is being used over here. As I said, should be a conductor introduced. So that is also important to us. With that only these factors will be there. Next, I can use one rule which is the FRH rule. Fleming's right hand rule. I guess I taught you FLH also. Correct? Fleming's left hand rule. Right? Here it is. Fleming's left hand rule. When I have a magnet I've placed with the conductor inside, that is the Fleming's left hand rule. Correct? And right hand thumb, which is for the rod one. And now I have FRH rule for the Fleming's right hand rule. What is this now? This will help us to find the direction of a current in the conductor. How? Again, in when you're having your entire circuit going on, again you make your fingers look like this. Thumb shows the direction of force. First finger shows the direction of the field, and the middle finger shows the direction of current. So direction of force, field, current are shown by these three fingers, but on your right hand. Okay. So the first finger shows the direction field, which is this one, B. Then the thumb shows the direction of the motion. Sorry, direction of motion or the force, which is F. And the middle finger will show the direction of current, which is I. So this is how the things are shown. So you can use the Fleming's right hand rule for this one. Then for EMI you can use it. Then Fleming's left hand rule you can use it for your when magnets are I'm putting a conductor through it. And for your straight conductor for checking the magnetic fields and direction, you can use the right hand thumb rule. Okay, so I hope whole chapter clear, and the mind map is there in the second slide. Okay, now we are going to do the simulation. I'm going to show a live simulation for the electromagnet induction. I'll show you that how is that actually working. So let's move towards our simulations. So students, here we are with the simulation for Faraday's law of electromagnet induction. So here you can see in the simulation I'll be doing with the 1 and 2 both the loops. So first one, let's take a voltmeter so that we understand about the voltage, how is it going. And even, okay, so here see this first one. What I'm doing is that I am taking north front, I'm taking it near to my circuit. So what can you see? The bulb is glowing. Correct? The bulb is glowing. What's happening? See the voltage meter as well. It changes as soon as I go. So what can we observe from this? We can say that there is voltage. The galvanometer will show some deflection as well. Even even this whole structure even shows us that when there is magnetic field, see here, when the fields are, now let me show you the fields also. This is my fields. So what's happening is all the field lines are present and even there is voltage introduced. Now if I remove, nothing is there, correct? But if I take my magnet near to the conductor, so what happened, there is voltage introduced. Same happens if I have two of them also. So if I have two of them, see this. In both of them here, see there is deflection also in both of them. Now if I flip my magnet, if I flip my magnet, then see this. See. So this is how what was the entire chapter about. Okay, this was the Faraday's law of EMI, and we had studied about electromagnet induction. Then we studied about the fields and everything we have covered up. All right, so students, thank you so much for watching today's video. I hope you enjoyed and learned many new things, and we had a quick revision also. I'll be seeing you in the next video where we're going to discuss some very important questions of magnetic effects of electric current, this chapter, and I'll be seeing you very soon. So till then, take care, goodbye, and don't forget to like, share, and subscribe, and comment, and if you have any queries. So students, bye bye, take care.